Hi guys, we have all used navigation apps like Google Maps or Apple Maps to go from point A to point B and navigate ourselves when we are driving. And we have all used delivery apps where we see how food gets delivered from the restaurant to our location from multiple drivers doing multiple deliveries. But probably everybody does not understand what are the mathematical building blocks and what are the software building blocks of how this routing is done and what are the constraints that these routing algorithms are optimized for. So today we are going to learn a little bit about that from Anirudh.
Hey Anirudh.
Hi.
So can you help us understand how we can go about understanding the technology behind routing, behind allocating of drivers, vehicles to logistics use cases?
Yes. So from a technical point of view, there are three building blocks. There's a routing engine, there's an optimizing algorithm, and there is a fleet orchestrator. Let's go into each of them one by one. So the routing engine is the one that understands the actual geography, like the latitude, longitude of where to go, point A to point B. What are the different types of roads that are connecting it? What are the different roads that are possible? What are the different routes I can take from point A to point B, and what are different roads that are connecting? The second thing is the optimizer, the optimizing algorithm. The thing here is you may not always want to do shortest path first. At times you may want to be like, hey, there's a high priority item that is far away, not on the shortest path, but I need to really go there and get that. So you may have prioritization, let's say by the time the order has been placed to connect, the weight of the good, the capacity of the vehicle, and you may want to optimize for different things. So that an optimization function has to be able to optimize not just for the distance, even other examples could also include fuel, time window and stuff like that. So these are the different types of optimization we would need to do. So that's the optimizer algorithm. The third part is a fleet orchestrator. What the fleet orchestrator does is it's not just optimizing for just one single unit, it's optimizing across the vehicles that you have. For example, should I spend two small vehicles of half the capacity and go and collect, or should I send one big vehicle of double the capacity and go and connect? So I need to optimize across my different fleet and not just at single vehicle point. So these are the three building blocks of a routing algorithm.
So what is the difference between routing engine and optimizing algorithm? What are the different ways that these two operate?
Right. So basically a routing engine just says like, hey, if you want to go from point A to point B, these are the different routes that you can go. And each of these routes, you are going to travel this much distance. It's going to take this much time, and you're going to be able to collect goods of, that have this priority. But the algorithm is the one that decides that, okay, I have 5 different routes. Which one should I pick?
Okay.
So the algorithm decides that.
Okay.
The routing just gives the inputs and it gives you different alternatives. So think of it like the routing is supposed to be able to create a solution space for you and tell you like, hey, these are the different permutation combinations that are possible, and the optimizing algorithm is the one that is checking, okay, which is the one that I want to choose.
So the optimizing algorithm takes all the possible routes as an input, but it also takes time, distance, weight, vehicle capacity as an input.
Correct.
And understands the objectives that you are pursuing.
Correct.
For your particular use case and recommends the best scenario.
Correct. And they both talk to each other, and the constraints is understood better by the optimizing algorithm, and the routing engine is the one that actually does the routing part and says, okay, as per your constraints, route A, route 1, 2, 3, 4 have the same A to B, but they are also sticking to the constraints in a different way.
Right. And how much flexibility do we have once we have these components to change our optimization objectives?
Right. So this again depends on the exact specific implementation. So even the routing engine will pre-compute some data and keep it ready for the next thing. And unless the underlying parameters change, for example, for routing, let's say the road availability or road availability for vehicle type, or sometimes you have like, okay, I want to take toll roads, I don't want to take toll roads, and you want to say like, hey, this road is broken for this type of vehicle and not this class of vehicle. So each and everybody is optimizing in a certain way so that, hey, most of the information I want to like pre-compute and keep it ready, and do like at inference time, I want to be able to not touch those underlying things. So that's where when you have something like, okay, the road conditions change daily, the fleet conditions change daily. I was optimizing just for weight, but today I want to start optimizing for even the category of the good I have. So these things always trigger like,
or the type of fuel I'm going to use, whether diesel or petrol.
Right. Exactly. Like your fuel prices change, so you want your optimizer algorithm to know like, hey, this has changed now. now compute from tomorrow onwards in a different way. So the way we would want to design it is like, some things are static, as I said, like these things don't change too much. But what is super dynamic is like, let's say your collection points, where I need to go and collect, which depot I am in today, because fleet breaks down, you have to send them to the garage for fixing, and then you have to bring down. So these things change a lot, right? So the way we do it is like, we have like a pre-computed information which don't change very often, handled separately, and things that we know will change very often is like fleet availability, where I need to go from point A to point B. These things keep changing very dynamically.
And the fleet optimizer takes these two things as inputs and then gives you a finalized route. Is that what it does?
Correct. So they all three are working with each other. They're all constantly talking to each other. What is clearly defined is which part of the problem is going to be solved by whom. So the final answer will be again optimized in such a way that's across everybody. The fleet optimizer is essentially like, hey, I can't optimize just for vehicle level, because then I don't see the big picture. And then I may not come up with clever solutions like, hey, why am I sending a vehicle of a smaller capacity there instead of sending 3 small vehicles? So on some days, if you're, let's say the price is like, okay, diesel has come down and these things are better to be done by a bigger vehicle, you'd want to do that. But let's say if the price of the petrol comes down and you're like, hey, my smaller vehicles are using petrol or EV, so now it's probably makes more economic sense to do that, and I'm optimizing for that. So then your fleet orchestrator will say that.
So what is then dynamic route optimization?
Right. So dynamic is when, as I said, the things that are changing very frequently are like, hey, where do I need to collect from? Where do I need to park my vehicle after collection happens? And is my road breaking or not? Because sometimes roads are unpredictable. Either you may want to say that, hey, I don't want to take a few roads because I know for a fact that there's always a lot of traffic here, so I want to avoid this. I want to avoid these areas. So these things keep changing very dynamically. If there is a road broken, then it's going to be broken till it gets fixed. So you may want to just come into your system and say, hey, this road is broken. Don't take it till I tell you, like, okay, this road is possible.
So if somebody wants to get into the statistical models and the mathematics and the software implementations of these,
right?
So how can one get started?
So there are quite a few here, and they're all experts at their own thing. From a planning perspective, you have PyVRP and OptaPlanner. These are very good tools for you to get started and understand, like, okay, how to actually optimize across this thing. You will get like a very good bird's eye view. And there are specialized tools. For example, OSRM is there, open source routing machine. There's also another routing machine by Google, open source one. So both of these will help you understand how actually the complication of routing really is. Like, it's not always, because we use Google Maps, we think like, okay, shortest path is always the right answer. That's not always the case. As I said, goods could be of higher priority, there could be a time window, and you may want to pick differently. So you have to be able to propose routes that are not always the shortest path, but are weighing some other constraints that are on the business. Open source routing machine, OSRM, what's probably called as, and the open OR tools by Google. These are pretty good tools for understanding the routing one, and also the underlying, the map data that you import into the system. There's a very popular tool called OpenStreetMaps. OpenStreetMaps is also like off-the-shelf product competitor to Google Maps, but you also can go in and build your custom maps, and you can inbuild, like, let's say if you're doing some survey and you have some raw data that you want to import it into, and you have your own survey data that you want to be able to enrich a popular data with, then the open source maps allows you to do all these things.
And what is the format in which this data is available?
Right. So PBF is what OpenStreetMaps takes. PBF is protobuf, which is essentially a very good protocol for storing data. It's optimized for data redundancy, data corruption, and it's a very standard data protocol to exchange in your microservices architecture and data engineering pipelines. It's been adapted specifically for OpenStreetMaps. OSM does it that specific way. So on map data, the complications are like, hey, we can say something is toll road or not toll road. We can say something is like, what is the width of the road. We can say things like, hey, is this road passable or not? Is it broken or not? And we have things like, this road will give priority when there is an ambulance or not. And you will have, like, even a road could be split into lanes. How many lanes are there in a road? And you will have like, okay, this lane is only passable by cycle. So there are many complications when it comes to roads, and roads have different metadata. So this is why OpenStreetMaps is an open source alternative for being able to handle so many different real world problems that we have.
Understood. It looks like the science and the software engineering behind being able to write algorithms for optimizing for road and fleet is very complex.
Yes.
So, do you have any words of encouragement for people who are trying to get into this from a software perspective?
Yes, it's exciting, but just understand that from the outside, because we are used to the Google Maps kind of an interface, we kind of feel it's very simple because Google Maps comes up with roads in like absolutely no, like in a fraction of a second. So we have assumed that it's very easy, but once we get into it, we start understanding the problems. And yeah, engineers love to solve problems. So if you feel like routing algorithms is this geography, and you should not be very afraid of getting into maths. So when people who are like that, the more down you go, the more statistics you will have to start understanding. Just like not get scared when mathematics comes into picture. And because these all algorithms, these are not generative AI, these are more like statistical models and stuff like that. And these the classic science, the classic maths is good enough to be able to solve these problems. These are heuristic problems. These are classic NP problems. You can't get them right in one shot. You have to do multiple iterations, and then based on what constraints that you have, you have to have an optimizer algorithm come in and say, okay, this is what I want to choose. So it does get quite interesting very fast.
All right. Thank you so much.
Thank you.